Alright, hello world. I didn't get a chance to really look at these again, but this is the page we're on. We'd done 35 last time. 36 is actually not bad. I think I'm just going to skip it for the sake of, you just group things, like if you were to do 3, you'll have x1 plus, and then you group these two together, and you use the previous result. And you'll see some stuff. There's a little bit of cancellation with a factorial, and, it'll pop right out. So it actually just follows from the multinomial theorem. You don't have to actually show this because the proof for this part also involved the binomial theorem. So if you've got the multinomial theorem, the same thing applies. You're going to get this as well. It's kind of an easy one. You'd think I would write that one down and take the W, but that's okay. Let's move on. So I did do 37 and 38 last time. 39, well, anyway, 39 is what we're on, and let's see how we do. I didn't look, I glanced at an answer for 39, but I don't know it. In fact, there was a weird factor that I didn't understand. So I'll spend a few minutes on it and move on if I don't get it. 39 is this sum. It's a finite sum up to n, and then it's saying this stuff equals n plus 1. I believe, so like the 2 and the negative, these factors sort of, I think they show up in the normal way. I'm looking at 39, I want to show -1 to the n minus k, 2 to the 2k, and then you've got n plus k plus 1. Choosing only odd stuff, the sum of that equals n plus 1. 0 to n. Yeah, there was an extra factor like negative x squared or something being multiplied in the answer that I don't understand. But we're going to see how far I get just trying to do this off the top of my head, which is probably going to be not very. So yeah, it's your sort of typical expansion, like what if I had something to the n? See, I'm already like stuck because I'm like, why are there only odd terms? But this almost matches up. So like if I took let's say we had a half, and then for x we'll do something like, I'll get this extra negative. Yeah, I'm not sure. What if we had something like 2z, and then we raise it, I want to raise it to this power. Alright. Why is it squared? Alright. Yeah, how am I going to get n? Yeah, I just don't get it. Like, I want to do this and see what happens. But then this isn't going to match up. And neither does the 2. But let's see what this gives me. And like, really? How are you going to put a k in there? Alright, so what if it was, I just don't know. This is going up. We have 2 squared. Like this is almost normal, right? Like, anyway, the rest of my thought here is not terribly relevant, but you'd have 2z to the, say, k, and then you'd get some term, but like, you can't do that. I mean, we can do it and then change, have a different index, but like, I don't, this is stupid. Where is this coming from? I mean, suppose we had like 4z to the n. Let's just look at that real quick. You'd get 2 to the 2k, z to the k. I guess we could have, we could make the other term negative, we could have done like 4z minus 1 to the n. So you get something like this. And there's a term here, obviously. And choose whichever you want, k or n minus k. But then this thing, I mean, like at 1, you're just getting 3 to the n to get rid of this thing, which is cute, but not what we were after. So yeah, I'm not really anywhere near it, huh? This is not a very highly skilled statement. This is just the binomial theorem. I mean, where is this coming from? Well, alright. So if we look at the answer, what was this, 39? It says each term of the left-hand side is the coefficient of this particular guy, right, in this expansion. So that's what's annoying. I was like, oh, well, yeah, duh. Right? That's an obvious statement. The only part I didn't get was this negative x squared, so we're going to have to look back at that. So we should consider the coefficient of this in, and then he writes down this sum. So he's summing. There's sort of a, yeah. See, really not so bad, right? I still don't know where that comes from, but we'll have to check. And then Oh, he summed it, right? I was going to say, like, where is this coming from? I still don't quite see that. Did he factor? Of course, he factors this out. And yeah, don't quite see it, but like you can see, in fact, I see this front matter, um, this difference over this. Yeah, I don't quite see that, but I mean that's clearly the sum of this stuff. I'm just not, yeah, I don't know. So yeah, it is kind of obvious, but he's summing over, and then he's using this as a separate series, I guess. Kind of confusing for me. So like your instincts would be like, oh, I clearly need to, raise it to this power. Um, so yes, it's the coefficient of 2k plus 1. If I had I realize I just read it, but I don't remember it. N plus k plus 1, right? Something like that. 2 to this odd power is part of the, right? And then he has, so that's where the half came from, to turn this into 2k instead of 2k minus 1. This goes to n plus, see, now I'm already, well, whatever. Keep moving. We can do like 2 to the j, x to the j, and then over here we've got n plus k plus 1, choose j. So at this odd value, we'll get this part. We won't have the alternating bit yet. Did he do it by subtracting 1, or did he actually? Oh, whoops. No, he didn't. Yeah, that's multiplying by it. Plus there's the square there that I still don't understand. So he's literally just tacking on an extra. Wait, is it to the power of n minus k? Yep, it is. All right, fine. So he's just tacking it on. Like, hey, I don't understand why there's an x there, but we'll get back to that. So he's just throwing that in there. Which is fine because these are not changing. So what's missing now? I don't actually see anything missing, right? This stuff in brackets is the coefficient, the 2k plus first coefficient of this mess. Except for, no, that's right. That's right. Yeah, hold on a sec. Um, yeah, all right. So, yeah, so what I really don't get is he's actually, he changes, like he changes the value of x for some reason. It's like he wants to make this j plus 2, but I don't get it. So for one thing, um, just for this one particular coefficient, 2k plus 1, you'll get um, you'll get the stuff in brackets, right? And so we're supposed to be summing as k goes from 0 to n. And that's where I'd kind of like stall. Because I just want that one particular. You want me to take a double sum? I don't really understand. Um, just the 2k plus first coefficient. So I suppose if you want, I mean, I don't get it. I mean, I can't really take the 2k plus first coefficient anymore if I've summed it out. So it's not like I can alter the order and then like after the fact look at a particular um, you know, look for like j minus 1 over 2 or something. Hmm. Yeah, I don't get it. We can write this, but it doesn't. I don't know how we're supposed to get that one particular. I mean, I follow it at the moment. I'm just going to be stuck on how, like, what else. General term on the left is the coefficient of the, this odd coefficient of this junk. I still don't understand the negative x squared. The negative I get. Did I write it down wrong? No, no. No, it's fine. I think it's fine. Yeah, 2k plus 1. So anyway, yeah, I can't argue with this except for I don't understand the x squared. So we'll look at the coefficient in, and then he just sums it. Oh, right. Did I never write down? Huh. Okay, I see. No, I still don't get it. No, it's fine. So like, yeah, he says just look at coefficient of this guy again. But obviously he didn't leave this as a sum. But he's saying we can look at 2k plus first coefficient of this, right, as a function. That's obviously a lot less unwieldy. I still don't get, he's got this to the n minus k. So we're getting like this extra term. Like this is an extra factor. I just don't understand why. Because I didn't need it. And what else is my problem? Each term on the left is a particular coefficient. I guess this is the other part that I'm confused on. Like, we're going to sum. How am I supposed to take the one where the k is 2k plus 1? Like, that doesn't make sense. Oh, he doesn't. He said it's 2n plus 1. Right. Yeah. You idiot. You wrote it down wrong. Awesome. Good. 2n plus 1. Cool. So that would still be fixed. That makes a lot more sense. But still, what is going on with the x squared? And then, then he evaluates. So, damn it, Dave. N. Oh, you wrote it down wrong. Did I really? I didn't. I didn't write it down wrong. Huh. Back to the drawing board. The general term on the left-hand side is the sum of the coefficient x to the 2n plus 1 when you expand this. Yeah, that was my confusion, I guess. So I wasn't wrong to say this. That's what matches up with his statement, but it's not what he's saying. He's saying the left-hand side is a coefficient for 2n plus 1. General term of the left-hand side sum is the coefficient of x to the 2n plus 1. Do you think this could be a typo? I don't think so. It makes more sense as 2k plus 1, right? Yeah, 2n plus 1 makes no sense here. Oh my god. Maybe this is why there's an x squared there. He's like scaling it. This is why there's an x squared there, huh? He's doing this. He's like correcting for this part that I'm all confused about. So first of all, he did this. He's multiplying by this, which I didn't understand. I took the -1 out of it, and then I've been complaining that it doesn't match up right. This effectively adds 2k and subtracts 2n. Well, in any case, suppose you had a term like x to the 2k plus 1. When you do this to it, it absolutely exchanges your x to the 2k plus 1 with x to the 2n plus 1, right? So it's doing what he just said. So that's why that's there. That's a crazy trick. Right? That evidently is like just enough to make this problem doable. That's wild to me. All right. I agree now with this there. Sure. So never mind all this stuff. I agree with part of what you're saying. We get here, and then if we put -x to the n minus k here, now what's true is that this chunk matches, well, I should say the 2n plus first coefficient is the original, question, the stuff in brackets. But you need this as well. Like you need that there as well. So if we sum over all of it, and we take the 2n plus first coefficient of the result, that would be the same. Okay. Yeah, n is fixed. It's magic stuff. All right. That's man, that's a crazy trick. Oh, you forgot to put the 2 there. There's a 2 here. So it's 2n. So when it hits against x to the 2k plus 1, it becomes 2n plus 1 instead. Alright, so yeah, there's a 2 there. Don't forget that. Alright. So if I was trying to sum this, what can we do? I remember him factoring, right? Like he factored, I don't know why the half would need to be there either. Let's pull the half out, I guess. But he pulls out n plus 1 because that part doesn't really depend on k, of course. So we've still got to sort of sum these up. But that's just, well, it would just be geometric except for this stupid term. And that's the other thing, like, this is almost binomial, right? But not quite. Yeah, I wouldn't know what to do here. If this term wasn't there, I mean, alright, whatever. That's fine. You can pull out part of it, right? You can pull out the n. So I got negative x squared to the n, and then we're summing this geometric thing. Oops, what are you doing? No, that's right. It's to the negative k, so you could write negative x squared and then raise it all to the k. Is that all he did? He didn't do it quite this way, but there's nothing really wrong with this. Alright, feels geometric to me. Oh, it's finite. Sorry, okay. So, in that case you'll get our junk out front, this extra factor, and then here you're going to get like, yeesh. This is a bit of a nightmare, isn't it? Well, anyway, you get stuff to the n plus 1, and then on downstairs you just get stuff. This is the stuff that I'm talking about. So you think that's all he did, is just simplify this? Let's see. N plus 1 I factored out, right? N plus 1, negative x squared to the n. The sum I already took care of, supposedly. So it's 1 plus 2x over negative x squared. And then upstairs is the same thing to the n plus 1. Yeah. Alright. Let's see if, like, half a second of algebra will make this the same as what he has. So I guess I'm adding. Let's just look at this chunk, you know. Downstairs you've got, you know, x squared plus 1 plus 2x over x squared. Yikes. And then upstairs, well then. I mean, this is cute. I don't remember this showing up in his answer. I mean, yeah, sure, fine. If you really want, we can keep going. But so what is this? Junk to the n plus 1. Like, this is our denominator upstairs. So you're looking at that minus, I don't know why I didn't just write it as one piece, but, and then when you're done with that mess, you can multiply by this. It just seems silly, doesn't it? Um, so we've got a negative floating around, which I'm going to get rid of now. We've also got x to the 2n plus 2 downstairs, but there's an x squared upstairs. So I guess I'm going to write it like 2n, you know? That takes care of that. And then we've still got this mess. And upstairs, well, didn't do anything with this yet. I guess, nah, I don't want to factor because there's not a negative over here. So we could factor one negative out if you want and make it a plus, but I don't see that helping anybody. I'm getting this for some reason, but that doesn't sound right. His looked a lot better than this. Alright, I'm going to take a look at what he wrote. On the other hand, this cancels, right? Some of this cancels. There's an extra negative sign. So like this stuff out front now matters a little bit, you know? So we're getting... Oh, he distributed... Did he distribute this? No, I don't think he did. He left this part out front. Yeah, that doesn't help anybody. But this he might have incorporated because it cancels that. And negative 1 to the n, Alright. So leave the half and leave this. But go ahead and just, you know, multiply this through. Negative 1 to the n pretty much cancels with this and leaves you with 1 negative, which I guess I'll put over here. Right, like this. I didn't fix this yet. I don't know what we're doing with this. But the x to the 2n cancels, and the negative we just took care of here. So it pretty much cancels, and there's an extra negative that I put over there. I left myself a giant space for no reason. So yeah, that's what I get. We could probably go further. X to the 2n plus 2. Alright. Time to see what he did. We're fine with this. Oh, right. When we're done with all this, it's still just the 2n plus first coefficient of the result. So I got that out front. Oh, wait a minute. That's the same. That is the same as what he has. Yeah, awesome. Awesome. Wait a minute. X squared plus 2x. No, that's what I got. Yeah. He just factored downstairs. Awesome. This is x plus 1 squared, of course. Okay. So with a lot of hand holding, I made it. This stupid factor was the whole trick. I don't know. I guess it's a trick you're just going to see when you're dealing with these series now and then. Consider coefficient in, boom. Okay. Division leads to polynomial degree 2n. Wait, what? Where the remainder is such. Coefficient in blah is equal to this. What? I was glossing over this power series comment, but But now I wonder if that's how he actually got to this. He's saying this is the power series for this. I can't like just factor that. It looks like that's what he did. But there's an extra term here. So if you factor it here, you're going to have to also, there's a term here with like a 1 plus 2x in the denominator suddenly. So I don't really follow this statement, but that's clearly what he divided out to get this ridiculous remainder. Right? I can't do it there, but like, I agree that it would be a polynomial of degree 2n, I guess. Of course, if I believe you, that means I believe 1 plus x divides 1 plus 2x. Oh, no. The remainder is this. Sure. Good. But, how's he getting this? How's he doing that? Like 1 plus 2x to the 2n plus 2 divided by 1 plus x squared. Is he really doing long division on this somehow? Yeah, I don't get this remainder. The remainder is blah. You get your polynomial of degree 2n, and then you also have a remainder term. Then you also have this remainder term that is f 1 minus 2n plus 2 2x plus 2, right, over your divisor. Is it obvious that this is what you would get? So yeah, so we had this to the 2n plus 2. He's kind of ignoring this for some reason. Well, that makes sense. It's just some polynomial. But yeah, why would he? So part of what I don't get is like just from the beginning he says it's a power series of this. And I'm like, well, all right, great. What happened to that x squared again? Yeah, it's so frustrating. It matches up perfectly except for the minus negative x squared to the n plus 1 term. Um, but that's not this. Wait, no, that's not this. Hmm. So yeah, there's a sentence I don't understand. Um, and then the coefficient, it's 2n plus first coefficient of this mess. This is our remainder, right? Yep, it is. Right. Yep. So, coefficient in this series is, yeah, I guess there's 2 here. I would have to do it out, but it can't be that bad, right? This is just 2n plus 2 times, well, 1, I guess. It could be alternating. So it's negative 1 to the, well, it's just negative. So it's a negative 1 times 2n plus 2. That's that bit. Is there a half there again? I guess it's this bit. And this one has an extra, like, power. So on the 2n plus first term, I guess that's where this number's coming from. Well, alright, let me check the last part. I don't understand his division comment. I'll buy it, but I don't, I definitely could not have repeated it. He's doing, like, he gets here and somehow divides. He does this division and gets a remainder that I don't recognize. But yeah, now that you've got the remainder, it looks like this. He's ignoring the other part because the polynomial is of degree 2n, so it's smaller than we care about. We want the next term. This part is, of course, well, it's like 1 minus x plus x squared minus x cubed, etc. It's just geometric with a negative x. So 2n, well, negative 2n plus 2 times this whole series, you know? So at 2n plus 1, we'd get a negative sign. We get sort of a double negative. We're getting plus 2n plus 2, which is correct. That's what he had written. Yeah, that's what he had written for the second part. So that's what comes from here. The 2n plus first coefficient. And then this part, you've got a half out front, but otherwise this is, I want to say, it's actually very similar. It's just it's just one derivative of this. So you're going to get, I mean, normally I would have put like k plus 1 x to the k, but instead we have negative x. Yeah, we got a problem here. I think there's an extra negative there. There's an extra negative popping out because this is negative x. But anyway, this is to the k again, and there's actually like a negative 1 times this because I took the derivative of this, you know? So you get negative 1 times blah. Although, now I'm wondering why this is here at all. I guess it's not. Never mind. It would happen on the next pass. Yeah, it doesn't happen now. Yes, it does. It happens from here. It happens because you took a power rule against this series. So you get 2x minus 3x squared, etc. Yeah. So the negative is the only contribution that this part has. You get negative stuff squared. That's this left-hand side. It's equal to, yeah, so this is there. This is there. I'm sorry. But anyway, we want the 2n plus first power. So at k equals 2n plus 1, we get 2n plus 2 right there. We're getting a negative as well, so we're getting negative half 2n plus 2 plus this part. And that's what I would get for this part. Negative half 2n plus 2 plus 2n plus 2. Alright, so if I can, I'm going to have to quit. Probably. Or maybe I'll try to look at the next one, but I'm not going to understand this. I mean, I agree that division would give you some polynomial of degree 2n, but how did he get the remainder so easily? Must just be something like obvious, right? So he looks at this power series instead. Like he looks at 1 plus 2x to the 2n plus 2, and he's dividing that by our denominator, and he's claiming, I get the numerator being of degree 2n, right, because there's 2 degrees downstairs, but he's saying the remainder is, and he just jots down, well, basically this, half 1 minus 2n plus 2 to x plus 2. So that's the only part that I don't understand on this problem. Well, slow going this week. I was hoping I could move a little faster, but it's not happening. Yeah, I'm going to come back to that. I'm going to have to think about this. But let's at least take a look at 40. So yeah, show that this sum is this guy. Damn. It's like almost, okay, are these coming from derivatives somehow? Because like this part is just a binomial theorem. Unfortunately, it's sort of being scaled here. If we had like, like this is almost just the number 1 times this thing. But how are you going to put that in there? I don't know. Yep, so I would have to quit already on this one. Decompose the sum into 3 terms. This formula is obviously true. It's first and second derivatives. That's the only part that I recognize. So you're taking this and differentiating in P twice. What? I mean, that was sort of my instinct that you're different. I mean, obviously it looks like this, and you're going to differentiate somehow to get those 2 powers, but I still don't get what you're saying. If I differentiate twice, won't I just get like, here's the original. If we differentiate twice, I guess it's still 0 to n, but you get v times v minus 1, right? P to the v minus 2, q n minus v. And on the right hand side you get like n times n minus 1 times p plus q to the n minus 2. Now, he also specifically lets p be x, right? So on the right hand side you'll get like 1. So of course we're going to let p be x, q be 1 minus x. So you get the 2, I didn't write it down here, but you're basically getting n times n minus 1 on the right hand side, and on the left we've got this, we've still got these 2 terms. This has become x, and 1 minus x. So this part's matching up. I mean, I guess you could multiply by x squared if you want. Yeah, I'm still not getting this. We've got, on the left I've got v times v minus 1 over x squared. That's what's different about, you know, other than that, what are we showing again? Yeah, he's got this business, which I don't quite have. I mean, I do have a square. differentiate twice. I could have thought of that. And this part was obvious, the binomial theorem. So I could get here without really any struggle. But now I don't know what you're saying. This is also PQ over N, right? I don't know where this came from. I don't know. I'll jot it down. Show. We've got v over n minus alpha squared, and the rest is pretty normal looking. And the right hand side I've got x minus alpha squared plus x, 1 minus x over n. Is there anything else I can... Some of this stuff doesn't make sense. No, you still go from 0 to n. I don't think he did any re-indexing because this is the same. And I can't move this. I can move the n's, I can move the x. But yeah, we're supposed to be showing this. And I don't think he has anything else really to say, right? Well, I skipped the first comment, which probably would have helped. That could be the whole explanation, actually. So I did think of scaling this right away. I was like, why don't we look at v minus n alpha instead? If you did have v minus n alpha squared, right? I don't quite have n squared, but close. But anyway, this, if you square it, is that what he did? Seemingly, yep, that is what he did. Alright, alright. Yeah, I don't quite see it. I mean, obviously we've got that term. Is that all he's going to do, is replace this with this mess? So yeah, if you expand this, you're getting v squared minus 2nv alpha, and then plus n squared alpha squared. It looks like he did more. Did he factor v out? I don't know, I don't see that, but clearly he did. Oh. Yeah. How did I screw this up? V squared minus v? Oh, he subtract and add v or something? Yeah, he did. That's odd. Yeah, he did. Why is he doing that? I mean, I don't see this, but he's trying to make it match up with this, probably. So for one thing, he has this. He subtracted v, then he added v in a goofy way. He's factoring it here, so we of course still have 2n alpha, but here's him adding v. Right? Okay, sure. So I divide this by n squared. It's still... The only reason I'm saying to divide by n squared is because this doesn't match up with what we had until you divide by n squared. But but okay. So yeah, let me read what he actually wrote. Decompose the sum into 3 terms, according to this. Um, hmm. Hmm. Oh, right. So there is this factor out front, right? Um, he's going to split that factor into these 3 terms, is what he just said to do. Um, so, anyway, from here, if we had 1 over n squared times the stuff we just jotted down, we would have that factor out front. It's part of our sum. And it's evidently equal to 1 over n squared times this stuff, right? Divide this by n squared. You'll get 3 terms. Yeah, I don't quite see it. 2n alpha minus 1 over n squared, and then this part just goes away, you get alpha squared. So he's saying take your series on the left-hand side and make it these 3. You still don't get what I have, but I guess that's good. I mean, I can see that this is true. Oh, he said like the first and second derivatives. He didn't just say the second derivative. He said its first and second derivatives will give you the 3 terms. Okay, so this is the second derivative. If I had done it once, you would get just an n times 1, effectively, on the right. And this is gone. So if you do it one time instead, you get the statement like v. Where does x come from? Oh, because I factored it out of there. Yep. So I'll keep that there. You get v over x, and choose v, x to the v. Is there a negative? Well, no, not on the right-hand side. There's not. On the... No, there's no negative. There's this power v that came from p to the v. But I also factored one of the, the p downstairs here. So it's not v minus 1. I fixed it by putting it there. I don't know if I... Well, yeah, I do want that there, I think. Alright, so there's your first derivative. Somehow between these two, I can, yeah, I'll get it. Our series is these 3 pieces instead, times this junk. The alpha squared part kind of takes care of itself. I'm supposed to show it equals this. Huh. I would have thought that alpha squared times this would just equal 1. Would just equal alpha squared. Maybe yeah, maybe it does. Maybe it still does. You could have just factored it. Could still be true. Some crazy trickery going on here. So it's this series, we're just replacing this chunk with all this. Why? Oh, and this is a constant, isn't it? This 2n alpha minus 1 business. So yeah, one thing I don't get is like I have an x squared and an x as part of my formula. I think he's just kicking it to the right hand side. And then like scaling by this. Because here's your here's your v squared term, here's your v term. That takes care of these two. This one's a constant. So yeah, it must just be a handful of algebra and it like somehow works out. Right? It's like at this point, this just kind of feels like a Calc 2 thing. We used to do, you could evaluate the sum of like k squared just using. So this is kind of a pretty common trick. Even this stuff is not that bad, what I'm doing right now. But I wouldn't have seen it. But that's interesting. Yeah, look at v minus n alpha, because it's easier to like square. And then at some point divide by n squared to correct for it. Anyway, we apparently have three terms. You can multiply by x squared. It's not varying at all, So I'm going to put the x squared over here. I'm going to put the x over there. And we're going to have terms 1, 2, 3, perfectly clear. So term 1 looks like, v minus 1 over n squared times this other stuff. But we have a formula for that. Yeah, I want it exactly in this form. So we're gonna put x squared over there, and then we're just gonna divide both sides by n squared. I'm getting x squared n minus 1 over n squared, like that. For term 2, I got this stuff in the middle with a negative sign. It's the sum of negative v, and then you got this stuff, right? 2n alpha minus 1 over n squared. And the rest is this usual. But we know that v with an x over it is equal to n, so the v part is just equal to nx. It's a negative as well. So I'm just going to divide by that as well, Right. I had this. Right, so on the right hand side, we're putting nx, and that would take care of just v, Yep. But then I want to multiply it by the negative of this stuff over n squared, like that. And then part 3 is a positive alpha squared times just the regular sum. So there's no v this time, it's just alpha squared, which is fixed, times nv x to the v, 1 minus x to the n minus v. So you're getting just alpha squared times whatever, but in our case, I think did I say this at the beginning? Maybe I never wrote it down. But because, you know, the sum of these numbers is 1, this series is just a constant times the expansion 1. 1 to the n is what you're looking at. So it's just that. So if we sum these up, evidently you're going to get this if you factor it. So we want to sum these, and that'll be it. Yeah, I don't know. He must be doing a little bit more trickery, huh? I'm getting x squared n minus 1 over n. I'm getting x times 1 minus 2n alpha over n. And I'm getting alpha squared. He's got like a minus x over n. Well, he's also got an x over n. Oh, minus x squared over n, excuse me. Hey, oh yeah, we have that too. All right. So part of it is, here's an x squared, and then there's a minus x squared over n. There's also a plus x over n, right? And then there's minus 2x alpha. That's it, minus 2x alpha plus alpha squared. So these guys we're grouping together as like x times 1 minus x over n. That's these two terms. And then x squared minus 2x alpha. Yep. It's just x minus alpha squared, right? Indeed. So that's 40. Wow. Impressive. Okay. That's a neat one. All right, ladies and germs, I'm going to go see if I can figure out what's up with this remainder. If it's easy, I'll just make a quick note on my YouTube about it. I won't necessarily make a new video. But if it requires an explanation, I'll just talk about it at the beginning of the next, my next stream. Either tomorrow or maybe Monday, something like that. You folks, have a great day. Thanks for popping in.